In this video, we're going to learn how to evaluate limits of absolute value functions. So here's our first question. We want to tell whether the limit as x approaches 0 of absolute value of x divided by x exists. And if it does exist, then we also want to compute the value. Alright, so let's think. What is the easiest method that we usually try to use to evaluate limits? Well, that's just direct substitution. So let's try that first. Direct substitution. So if we try direct substitution to evaluate this limit as x approaches 0 of absolute value of x over x, we just go ahead and substitute in 0 for x, so absolute value of 0 over 0. Absolute value of 0 is just 0, so 0 over 0, and oh boy, that's not good. 0 over 0 is indeterminate form. Okay, so we need to go ahead and simplify this limit a bit, because we can't just plug in for x right off the bat. So let's think back to how absolute value of x is defined. Absolute value of x actually has two branches to the function. It's a piecewise function. Now, when x is positive or 0, the absolute value doesn't change anything about x. So we have absolute value of x is just equal to x if x is greater than or equal to 0. But if x is negative, then the absolute value strips that negative sign. And the way that this is done, stripping the negative sign, is actually by multiplying by -1. If you multiply a negative number by -1, then that number becomes positive. So actually, absolute value of x, if x is less than 0, it's negative x. Where that negative really means just cancel out the negative sign that already exists in this x. So this negative x is really a positive. Now we want to compute the limit as x approaches 0, and 0 is the crossover point where we change pieces in the piecewise function. So we really need to split this limit up into two cases and check both of them. There's the case of the limit where x approaches 0 from the positive side, and there's also the case of the limit where x approaches 0 from the negative side. Let's think about that positive side first. So if x is approaching 0 from the positive side, then x is greater than 0, which means we are on this branch right here. So absolute value of x in this case is just equal to x. So we can go ahead and stick that in. Limit as x approaches 0 from the positive side of x over x. And x over x, that simplifies to just 1. So limit as x approaches 0 from the positive side of 1, and that limit is of course just 1. We can do a similar thing to solve this limit as x approaches 0 from the negative side. From the negative side, x is of course less than 0, so we're on this branch here, where absolute value of x is treated as negative x. So this becomes the limit as x approaches 0 from the left. Absolute value of x now becomes negative x, and that's divided by x, and negative x divided by x, that just simplifies to -1. So limit as x approaches 0 from the negative side of -1, which of course is just -1. So interpreting our results here, we see that the right and left limits are not equal. The limit from the right is 1, whereas the limit from the left is -1. And in order for a limit to exist, both the right and left limits have to be equal. So, therefore, the limit does not exist. So, there we go. We're done. The limit just doesn't exist. Alright, here's our next problem. We want to tell whether the limit as x approaches 3 of the square root of the quantity x squared minus 9 squared, all divided by x minus 3, exists. And if that limit does exist, then we also want to compute its value. So again, our first approach is always direct substitution. Because if it works, then we're just totally done. And that would be easy. That would be almost too easy. You can imagine it probably won't work, but let's try it anyway, just in case it does. So limit as x approaches 3 of x squared minus 9, the quantity squared, divided by x minus 3. If we plug in just 3 for x, we get square root of 3 squared minus 9, the quantity squared, all over 3 minus 3. So this is square root of 3 squared is 9, so we really just have 9 minus 9, which is 0, and 0 squared is 0, and that's all over 3 minus 3 is 0. Root of 0 is, of course, just 0, so 0 over 0. Again, this is indeterminate form. So, oh well, we tried. But there's no way getting around it. We have to work with the limit. We have to go ahead and simplify this expression as much as we can. Now, one thing to remember here is that the root of a square is an absolute value. So this limit as x approaches 3 of root x squared minus 9, the quantity squared, all over x minus 3, we can just replace this root and the square with an absolute value. So limit as x approaches 3 of absolute value of x squared minus 9 over x minus 3. And now to continue simplifying this, we have to go ahead and write down the piecewise expression for x squared minus 9. And to do this, we have to figure out where the crossover points are. Where does this expression inside the absolute value equal 0? Well, where does x squared minus 9 equal 0? That's like asking where does x squared equal 9, which is just at positive 3 and negative 3. So we'll have 3 cases actually. We'll have the case if x is greater than or equal to 3. We'll also have the case if x is between negative 3 and positive 3. And we'll lastly have the case if x is less than or equal to negative 3. So first case, if x is greater than or equal to 3, maybe just think, what if x is 4, say? And if we plug in x is 4 into here, we get 4 squared minus 9, which is 16 minus 9, which is 7. The absolute value of 7 is, well, just 7. So basically, if x is greater than or equal to 3, then this inside of the absolute value is non-negative. So we don't have to worry about changing the sign at all. We can just keep it as it is. So it just stays the same, x squared minus 9. And it's the same argument, actually, if x is less than or equal to negative 3. If we have, for example, negative 4, then if we plug in negative 4, we still get that negative 4 squared is 16. 16 minus 9 is 7, and absolute value of 7 is still just 7. So it's also the case that when x is less than or equal to negative 3, then this inside expression, inside of the absolute value, is non-negative, and we can just keep it as it is. So it stays as x squared minus 9. Now, if x is between negative 3 and 3, say x is equal to 0, then the inside expression in this absolute value comes out to be negative. 0, for example, 0 squared is 0, then 0 minus 9 makes negative 9, but absolute value of negative 9 is positive 9. So the inside expression here is negative, and we have to change it to become positive. And how we do that is we just tack on an extra negative sign. Because if this expression x squared minus 9 is already negative, then we put another negative sign on it, then the 2 negative signs cancel out, and we've got a positive. Alright, so let's go ahead and break our limit up into 2 of these cases. The limit as x approaches 3 can be broken up into the limit as x approaches 3 from the positive side. In that case, we have x is greater than or equal to 3, and the expression that we can substitute in for absolute value of x squared minus 9 is just x squared minus 9. So we can go ahead and put that in, just x squared minus 9, and that'll be over x minus 3. There's also the limit from the negative side, the limit as x approaches 3 from the negative side, and again, we just look to our piecewise function here. When x is approaching 3 from the negative side, we are right below 3, so we're actually in this regime here, where x is between negative 3 and 3. X is just slightly less than 3, so it's in here. And in this kind of regime, the expression absolute value of x squared minus 9 can be treated as negative of x squared minus 9. And then that's over the same denominator, x minus 3. So let's go ahead and compute these 2 limits. starting with the limit from the right, the limit as x approaches 3 from the positive side. So we can go ahead and factor that numerator there. Becomes the limit as x approaches 3 from the right. The numerator factors into x plus 3, x minus 3. It's a perfect difference of squares. Then that's over x minus 3 in the denominator. So we can cancel x minus 3 from the numerator and denominator. And then we just have the limit as x approaches 3 from the positive side of x plus 3. And we can just go ahead and sub in 3 for x here. So that's just 3 plus 3, which is 6. So that's our limit from the right, but how about our limit from the left? The limit as x approaches 3 from the negative side. We can go ahead and compute that limit similarly. So we've already got our limit expression, so let's just go ahead and factor the numerator. So negative of, we already know, x squared minus 9 factors into x plus 3, x minus 3. And then that's over x minus 3. So we can cancel out these x minus 3's from the numerator and denominator, and we've just got limit as x approaches 3 from the negative side of negative of x plus 3. And we go ahead and sub in 3 for x, and we get negative of 3 plus 3, which makes negative 6. So again, we see that the right and left limits are not equal. Therefore, the limit does not exist. So that's our conclusion. This limit just does not exist, because it comes out to different values depending on whether we approach from the right or the left. So now we know how to compute limits of absolute value functions. We just break them up into their piecewise representations, and then compute right and left limits accordingly. In the future, we'll continue learning how to compute tricky limits, because limits lay the foundation for two of the most important concepts in calculus, differentiation and integration.